Hi, my name is Anish Kodana, and today I'll be talking about Markov Decision Processes, also known as MDPs. MDPs are essentially a stochastic decision-making framework. They're able to tell us what action we should take at a given time, also known as a policy. MDPs are inherently dependent on the Markov property, which states that the conditional probability distribution of future states of a process only depends on the present state, not the sequence of events that preceded it. Essentially, future states only depend on the current states. There are several components involving in solving an MDP. The first is the state, which uniquely identifies the state of the environment at any given time. Next are actions, which we can use to get from one state to another. The transition model gives us probability distributions for each of these actions. For example, a certain action might only be successful 50% of the time. Finally, there is a reward function, which allows us to give the robot a motivation to reach a certain state. Because of this, MDPs need to have the constraint of full observability. In order to know all the possible states and their rewards, we need to know everything about the environment. The diagram describes the Markov property in action. As you can see, each state is only dependent on the previous state as well as the previous action. You might be asking yourself, why do we even care about MDPs? For one thing, they are extremely useful for decision making. Take, for example, the grid world scenario. In both the top and bottom cases, we have a starting position and an ending position. You might be thinking, why don't we just use a pathfinding algorithm like BFS or A-star to find the best path from start to goal? For the bottom case, this is simple enough and a pathfinding algorithm would suffice. For the top case, however, we map obstacles to negative rewards and the goal to positive rewards. Though we can use a pathfinding algorithm to find the optimal policy here, the pathfinding algorithms are deterministic. They assume that we will always get from one state to another state if we perform an action. In reality, this may not always be true. MDPs allow for stochastic decision making where there is randomness involved. We will see this behavior in an example later in the slides. To solve an MDP, we want to determine the optimal policy, which will maximize our expected value over a sequence of states, like a path. The expected value is a combination of the probability of reaching the state and a reward based on that state and future states. We're able to solve an MDP by calculating the value function, which maps the state to its expected value. From there, getting the optimal policy is simple. We just take the action that gives us the maximum value or utility. To calculate the value function, we can use the recursive form of Bellman's equation. On the left, we have the value function calculated after an infinite number of iterations, or at least until the value function is converged. On the right, the first term we have is gamma, which is a discount factor. We use the discount factor to signify how important future rewards are to the current state. A reward that occurs n steps into the future will be multiplied by gamma to the power of n to describe its importance to the current state. Now, we calculate the maximum value for every possible action. We add the reward function, which is dependent on the state and the next action, to this integral. Typically, the integral would be used when you have an environment that is modeled based on continuous data, like in real life, but oftentimes we must discretize the environment to process it, so we can replace the integral with a summation across all the possible states. The inner term of this summation will be the value of the state multiplied by the transition probability from the current state to the state given the action. Now let's take a look at an example. In this grid world scenario, each box is a state. We have 4 transition probabilities, moving up, down, left, and right with a probability of 0.9. We also have rewards for certain states. The red states have a reward of -5, the green states have a reward of 5 and 6, and the white squares have a reward of -1. We also use a discount factor of 0.9. We want to first initialize our value function. Each state will have an initial value equal to the smallest reward, in our case, -5. The terminal states will have a value equal to their reward, in this case, 5 and 6. Let's take a look at calculating the value for this blue state. We first multiply by 0.9, which is the discount factor. We multiply that by the maximum value across every single possible action, up, down, left, and right. For each case, we want to add the reward of the current state, which is -1, plus the transition probability for going up, multiplied by the previous value. In this case, the initial value would determine to be -5 for going up, plus the failure, which is 0.1, multiplied by the previous value of staying in our current state. We do this for up, down, left, and right, then we sum it up, and eventually we get that the value for the state is -5.4. Now let's do the same calculations for another state. In this case, we only have 3 values we do the maximum across, because we can't go up. We can only go down, left, and right. For going down, we do -1 plus 0.9, which is the transition probability of going down, times the value of this red square, which is -5, plus 0.1 times the value of staying in our current state, which is also -5. We do the same thing for left, but for right, we do -1 plus 0.9 times 5, because as we said before, the value of being in the terminal state would be the actual reward for that state, which is 5, plus 0.1 times -5, which is what we get if we stay in our current state. If we do the maximum and then multiply by 0.9, we get that the value for this state is 2.7. This is what we get if we do this exact calculation for every single square for one iteration. This is what we get after we do value iteration again. We calculated this by using the first iteration as the previous iteration in the formula. As you can see, our values are starting to expand. The 0.8 used to be a -5.4 in the previous iteration. These are the values we get after the third iteration. The values are still expanding, which means that our value function hasn't converged yet. After the 20th iteration, you can see that our values for each state are now all positive, but we still haven't converged. We finally converge after reaching iteration 100. Now we can choose a starting state and calculate the optimum policy to get us the highest reward. Let's start off in this state. If we look up, down, left, and right, we can simply choose to go in the direction that gives us the next highest reward. In this case, it would be going right to go to 9.67. If we do the same thing here, you can see we want to go right again. This time we can choose to go either right or up. We can go up and then right again, and finally right again, puts us at the terminal state with the highest reward, which is 6. Now let's take advantage of MDPs and switch things up. Imagine we have a robot that's really good at climbing up and down, but not so good at going left and right. This changes our transition probabilities. Up and down is successful with a probability of 0.9, and left and right is successful with a probability of 0.75. Let's compare the converged value functions for both sets of probabilities. On the left, we notice that the best path was to go to the goal that gives us a reward of 6. Now with the new set of probabilities, we realize that the best path is to actually go to the goal that gives us a reward of 5. This is because this path involves fewer left-right movements since we know the robot isn't good at those. We were able to dynamically solve the MDP to take this into account with a new constraint, something we couldn't have done that easily with a pathfinding algorithm. For some more information about MDPs, I suggest watching these short YouTube videos. They really help me understand the basics of MDPs. I would also suggest looking at this article, which helped me with the actual calculations. Finally, you can also take a look at the code that I used to calculate the values I showed in this example. Thanks for watching.